Hello, everyone. My name is Gamanji, and I am a cloud native leader, practitioner, and contributor. Currently, as mentioned, I am fulfilling the role of a senior Kubernetes field engineer for Apple, which pretty much means that I'm bringing my cloud native and Kubernetes expertise to different products within Apple and different teams. As well, quite recently, I've been elected as one of the TOC for CNCF, or Technical Oversight Committee member for Cloud Native Computing Foundation. Now, in addition to the TOC, as well, I have collaborated with Udacity to release the Cloud Native Fundamentals course, which is a free course and pretty much allows anyone with little programming experience to navigate the Cloud Native ecosystem. And in addition to that, I am performing an advisory role for Captain, which currently is a sandbox CNCF project. Now, today, I would like to talk about the bare metal Chronicles, and more specifically, the intertwinement between GitOps, Cluster API, and Tinkerbell. And to do so, I will start by introducing the Cluster API principles. I would like to provide the fundamentals for everyone to understand how Cluster API works, but more importantly, how it provides one interface to deliver your clusters to different vendors. Secondly, I would like to focus on the bare metal provisioning in the cloud native space. And for that, we have Tinkerbell, and it pretty much allows you to provision your bare metal anywhere. But more importantly, I will focus on the Cluster API Tinkerbell provider, which is called, well, capped in a way. So that is the provider which will allow you to bootstrap any machine as a Kubernetes node within a cluster. And for the first section, I would like to focus on how can we optimize the delivery of our infrastructure in an automatic fashion. And for that, I'm going to talk about GitOps tools such as Flux and Argo CD, and where exactly we can integrate it to provide that automatic reconciliation of our config. Now, before I move forward, just kind of a show of hands, how many of you have heard about Cluster API? Awesome. How many of you have heard about Tinkerbell? And I'm not meaning the character. Cool. And how many of you are using GitOps or have heard about GitOps before? Oh, that's actually good. GitOps it's in a good place. Now, before I move forward with the topic, I always like to introduce the ecosystem that allowed this kind of problem space to appear, but more importantly, this kind of problem space to be resolved. So if we look back 8 years ago, we had the container orchestrator framework space was very heavily diversified. We had tools such as Docker Swarm, Apache Mesos, CoreOS Fleet, Kubernetes, and all of them provided a viable solution to run containers at scale. However, Kubernetes took the lead in defining the principles how to run these containerized workloads. Nowadays, Kubernetes is known for its adaptability and portability, but more importantly, for its approach towards declarative configuration and automation. And we can actually see this in numbers. Based on the CNCF survey in 2021, which is last year, 96% of the companies are using Kubernetes in production or they're POCing it at the moment, which is massive considering that this tool has not been there 8 years ago and it completely transformed different industries and entire sectors. Now, when we look into the contributor community, we can see that we have a growing community there as well. More than 50,000 engineers are actively collaborating towards feature build-out and bug fixing. And when we're looking into the end-user community, more than 57,000 attendees were registered at KubeCon, which pretty much is a flagship event to gather all of the adopters, maintainers, contributors in one place. And seeing this community grow and seeing that the interest in these conferences grow showcases the growth of the cloud-native landscape. And this community, all of it together gathered to pretty much extend Kubernetes functionalities. And we're talking about different tools for service mesh, networking, runtime, storage. There's a plethora of tools at the moment. And this created what today we know as the cloud-native landscape, which resides under the CNCF umbrella. Now, moving to the first part of our talk, we had multiple tools that were built to extend Kubernetes functionalities. However, at the same time, there are multiple tools built to bootstrap a cluster, such as KubeSpray or COPS, Tectonic installer, which comes from CoreOS. However, if you look at all of these tools, it's difficult to find a common denominator. What it actually means is you can use one tool to provision your cluster, for example, to AWS, but you might need to use another tool to provision your cluster to GCP. And these methods are going to be completely different. And if you're an organization that has a multi-cluster requirement, that presents a challenge. And Cluster API was built with this purpose in mind, to simplify the provisioning of your clusters to different cloud providers. So when you talk about cluster API, pretty much this is a set of declarative APIs for cluster creation, deletion, management, and maintenance. But more importantly, it does so for different cloud providers. So when we refer to cluster API, we refer to SIG Cluster Lifecycle, which had its first initial release in April 2019. Since then, it had multiple releases, and just 3-4 months ago, they entered the beta stage. So they're currently serving a V1, Beta 1 API endpoint. And I mentioned that Cluster API allows you to deploy your clusters in different providers. And currently, there are more of a dozen of them, from which we're going to have the big cloud providers such as GCP, AWS, and Azure. They have support for Chinese providers as well. So if you had to deploy infrastructure to China, you'd know it's quite a challenging task because mainly you end up with a Snowflake infrastructure and a Snowflake deployment process. With Cluster API, they support some of the Chinese providers such as Alibaba Cloud, Baidu Cloud, and Tencent. And you can easily provide a cluster to these Chinese providers as easily as you do in AWS. But more importantly, we had a new initiative from the community to focus on the provisioning of bare metal. And this initiative is currently led by providers such as Packet and Metal Free. Now, let's look at how Cluster API works. Supposedly, we'd like to deploy a couple of clusters in different providers, different regions. The first thing you'll require is going to be a management cluster. Now, Cluster API, as a nutshell, it is known as Kubeception, in a way. You need a Kubernetes cluster to deploy other Kubernetes clusters. So we need one starting point. Now, for testing purposes, if you want to trial Cluster API, it is recommended to create this management cluster using Kind, which is pretty much a Dockerized version of your Kubernetes. If you want to use Cluster API in production, then it's recommended to use a fully fledged cluster. And this is because it comes with a more sophisticated rolling out strategy and recovery strategy. Once we have our management cluster, we'll need to install the controller managers on top of it. And there are currently at least 3 controller managers that you require: the Cluster API CRDs, the Bootstrap provider, and the infrastructure provider. Now, Cluster API introduces 5 new custom resource definitions, or CRD, and will require a controller to make sure that we can create, reconcile, and delete any resources we have for it. The second controller that we require is one Bootstrap provider. And this is the particle that pretty much translates the YAML configuration that we have into Cloud init script, and it will make sure to attach the instance to the cluster as a node. And currently, this capability is provisioned by kubeadm, Talus, and very recently, it's going to be EKS from AWS. And the first set of controllers that we're going to require is going to be the infrastructure provider. And this is the particle that actually interacts with the APIs from the provider and provisions the actual resources. We're talking about instances, we're talking about security groups, IAM roles, and so forth. So if you want to deploy clusters in different providers, you'll require a controller for every single provider. Now, once we have our controller managers installed, we'll be able to provision the target clusters. And the target clusters are the clusters that we provision to our application teams to deploy their services on top of. And these are going to be the clusters that the customers will interact with when they're using your product. Now, I mentioned that Cluster API introduces 5 new custom resource definition. And this is cluster, control plane, machine deployment, machine set, and machine. To declare a cluster using YAML, the first resource we need to define is going to be cluster, and this is going to take care of your networking components. We can specify the CIDR for your pods and services, any DNS suffix, and so forth. By default, and this is a change that happened less than a year ago in the Cluster API repository, by default, every single cluster resource is going to be associated with a control plane resource. So what it actually means that this resource control plane, it will programmatically allow you to manage a set of machines that have these control plane components installed on top of it. And machine is another resource that is pretty much similar to Node. We can specify the version of Kubernetes we want to run. We can specify the instance type for a cloud provider. We can attach any security groups and so forth. So now we have a cluster with a control plane. This is going to be the by default, step 1. Now, if you want to run any workloads, you'll require a data plane. And this usually is defined by using a machine deployment. Now, machine deployment, if you know Kubernetes CRDs or resources, machine deployment is very similar to deployment. Pretty much it will come with a very powerful rolling out strategy between the machine set resources. Machine set is very similar to replica set. It will pretty much make sure that you have an amount of machine resources up and running at all time. And machine, we've already seen this, it's the instance, which will run the Kubernetes binaries in a particular version, in a particular instance type in a cloud provider. And just for the example purposes, I'm going to show a cluster.yaml resource and how we define our cluster using this kind of configuration. I'm going to show two examples, one for AWS and one for GCP. But what I really want to showcase is the simplicity of configuring those and the reusability of the manifest. This is actually quite important. So here we have a cluster resource with the name demo cluster. We specify the CIDR for our pods, which is a /16 subnet. And towards the end, you can see by default, we have a control plane reference attached to our cluster. So this is going to be by default. However, to make the differentiation for cloud providers, I would like to draw your attention towards the infrastructure reference. So here we have an AWS cluster with the name demo infra. And what it actually means is this is going to actually pull a manifest with configuration specific to AWS that we can actually write. So here we have an AWS cluster. We want to deploy it in EU Central 1 in this region. And then for example, another parameter that we can choose is the SSH key that we want to attach to our instances. Now, very important, if we want to change this manifest and deploy a GCP cluster, these are going to be the only changes required. So in our cluster manifest, the only thing we need to change is going to be the GCP cluster. The kind is going to be different. And what we actually choose is a manifest that has parameters specific for GCP. So here, the region is going to be Europe West 3, which is very particular naming convention for GCP. We have the concept of a project, which in this case, we attach our cluster to a CAPI project. And then in addition to that, we can choose other parameters such as the network, in this case with the name default CAPI. And just as a recap, to provision a cluster of cluster API, we require a management cluster. We'll require all of our controllers, at least 3 of them. In addition to our YAML manifests, we'll be able to provision our target cluster. So once we apply those cluster.yaml and machine deployment.yaml, we'll be able to have a cluster which is going to be in AWS or in any cloud provider, really. Now, at this stage, we understand that Cluster API solves one problem for us. It allows us to deploy in a unified manner different clusters to different cloud providers. But more importantly, it introduces this concept of cluster as a resource. Pretty much we have YAML manifests that we can reuse, template, and do so much more with it, as we're going to see later on. Now, the growth of the Kubernetes ecosystem did not mean just providing or deploying your clusters to the cloud providers or public cloud providers. We have companies that are enterprise organizations and are very restricted in where they can run their services and when they keep their data. So for this kind of particular organizations, one of their requirements is to provision their infrastructure on bare metal. And if you want to provision your cluster on bare metal, Tinkerbell is going to come to rescue. But first, let's focus on Tinkerbell and what it actually provides at its base capabilities. So Tinkerbell is an open source tool that focuses on the provisioning of bare metal anywhere. It was built by the Equinix Metal team in 2019, and currently it's a sandbox CNCF project, so it's still at the beginning of its journey. But this is why I'm talking about it, because I want all of your interest to gather around it, and hopefully you can contribute and use it further. So Tinkerbell is going to focus on the maintenance, cost, and management of bare metal. When you're looking at its infrastructure, this is purely Tinkerbell. I'm going to talk about cluster provisioning later on. So Tinkerbell has 5 main components. The team actually likes to call these 5 microservices. The first one is going to be called Tink, and this is going to take care of the provisioning of bare metal. It has the CLI, it has the worker, and the server itself. Now we have other components which interacts with the Tink server. We're going to have Boots, which pretty much takes care of the networking components. It will configure the DHCP and iPXE server. We have OC, which pretty much takes care of the OS installation environment. So this will take care to install any operating system on your bare metal machine and any dependencies on top of it. Then we're going to have Hegel as well, and this pretty much takes care of all of the metadata that you store for your bare metal. And then we have an optional service, which is ppng, taking care of the boot and control service. But let's look how actually Tinkerbell provisions bare metal. For this, we'll require three main components: hardware, template, and workflow. The first thing we need to do is define what kind of hardware we have. It's not just about you have a piece of Tink and it automatically will identify itself. For example, if you have some Raspberry Pis, you'll need to identify those. And you'll need to write a JSON file for hardware saying that I have this machine with this particular unique MAC address. And you can have a list of those hardware available. Next, we will need a template. And template is a set of actions, pretty much saying we want these steps to be executed on this particular Tink server. So, for example, you want to install Ubuntu, you want to install any binaries for running your application. You can think about this as a golden image. That's kind of very similar. And workflow pretty much connects the hardware to the template. It will say, run this set of actions on this particular hardware. So a workflow pretty much, we can think about this as a pipeline as well. Once we have all of these three components, we can interact with the Tink CLI, which will take all of this configuration, we'll send it to the Tink server, and then by the end, we should have bare metal machines that have been executed with steps of actions. So our bare metal machines are going to be provisioned in the state that we want. Now, the next question is, we know that Tinkerbell can provision our bare metal anywhere with our requirements. How can we attach that instance to the cluster as a node? So in this case, we have a provider from Cluster API, which is called the Tinkerbell. It's Tinkerbell provider. So CAPI, or Cluster API provider for Tinkerbell. And this is how it works. I'm going to take you all step by step. So there are three main areas that we need to identify. What we need from the Tinkerbell side, what we need from the management cluster, and what our result is going to be, which is going to be a target cluster. So first of all, as intended, we need to have those three components: hardware, template, and workflow, and we have them. Now, the first thing we need to actually have is the actual hardware and define it within Tink. This is pretty much straightforward. Again, we need a Tink server to be up and running. It can be on your local machine or it can be anywhere else, as long as you have access to it. Next, for the Cluster API, we'll require a management cluster. Nothing changed there. We still require our Cluster API controller managers. So we require at least three of them. One for the Cluster API CRD, one for the Bootstrap provider, for example, kubeadm, and we'll require the controller for Tinkerbell. So that's why we have CAPI there. Once we have our controller managers installed, we'll require our YAML manifests, so the definition of our cluster. And in addition to that, again, like these two components, they are pretty much the same for Cluster API. However, to configure it to run with Tink, we need to provide our hardware YAML. So supposedly, you have 4 machines that are available. Cluster API does not assume that all of those 4 machines can be bootstrapped as a node in the cluster. Hence, we need to define the hardware YAML. We can say that from those 4 machines are available to be run as nodes in the cluster, or we can say only 2 of them are available. So once we have all of these requirements, once we deploy our YAML manifests, the CAPI controller, or the Tinkerbell provider for Cluster API, will pretty much run a set of templates and workflows. So what it's going to do, it will install the Kubernetes binaries on top of those machines. It will install an operating system, all the Kubernetes binaries, and by the end of it, it will be attached to the cluster as a node. And it will do it repetitively up to the point we have the desired state of machines for our clusters. And when it comes to the YAML manifest, just as an example to see that we can still reuse those YAML configurations, here we have a Tinkerbell cluster, which is going to be referenced. And by default, this is going to pick up a new manifest that we can define as well. We can parameterize accordingly. So this is going to be a Tinkerbell cluster with the name demo infra. And in this case, we can configure the image repository that is going to look for our images. Now, this is going to be for the OS installation. Cool. Now, this has been quite a packed session. We understand so far how Cluster API works, that it allows us to provision clusters anywhere. We understand that Tinker allows us to provision our bare metal anywhere. But more importantly, the combination between Cluster API and Tinker will allow us to deploy any clusters on bare metal. Now let's see how we can improve the developer experience. How can we introduce some automation to our deployment of infrastructure? And for that, we have GitOps in mind. Now you are familiar with GitOps, most of you here, but I still like to have like a very basic introduction of what GitOps represents. GitOps pretty much is a strategy that has Git repositories as the source of truth for the desired state of your application, and in our case, for our infrastructure. What it actually means is by default, we're going to have a PR-based rollout. The difference between our local environment and production is just one PR away. With GitOps as well, we have the feature of automatic reconciliation. So GitOps tool will look for a repository, and if new commits are identified, these are going to be extrapolated and applied to the cluster straight away. But more importantly, with GitOps, we have a version state of our cluster. We have different data points of different states of our cluster. So if we are in a failure scenario, we can easily revert by using a git command. So that is a massive improvement to the developer experience and to the recovery process. Now, when we look into the cloud native space, the GitOps capabilities are offered by two tools, which is going to be Argo CD, and Flux CD as well, depends how you want to call it. Both of these projects are currently incubating, but both of them are applying for graduation within the CNCF. And to reach a graduated state means that you have a growing community, and more importantly, a healthy community. You have different companies contributing to your code. So if both of them are going to reach this status, it's going to be a massive milestone for the cloud-native landscape. Now, removing the Tinkerbell from the image, how do we improve the deployment of our cluster with Cluster API and Argo CD? So currently, on the management cluster, we still require that. On the management cluster, we have our controllers, we have our YAML manifests. But more importantly, this YAML manifest we can store in Git, which is a very important component for GitOps, and we can parameterize them. So for example, we can use something like a Helm chart or customize to parameterize different variables that we want. So we have those five custom resource definition. What I chose to parameterize is the Kubernetes version. Here is going to be 123.4. I can choose to parameterize the numbers of our master and worker nodes. So I'm going to have 3 masters for our control plane and 1 node for our data plane. Another thing we want on our management cluster is going to be the Argo CD server. So Argo CD pretty much is going to be installed in the management cluster, just for the kind of demo purposes. And what it's actually going to do, it will look at any changes we have for our Helm chart. For example, if we want to increase the number of workers to 2, Argo CD will identify that commit. It will apply to the YAML manifest. The Cluster API controllers will pretty much identify these changes and deploy new machines to match our desired state. And this, in the end, will result to the change of our target cluster. If we introduce Tinkerbell in all of this image, pretty much what we have here, we still need our hardware, we still need our Tink server. Now, on the management cluster, we're going to have the controllers. We're going to have a Helm chart to manage our manifests. We're not going to have the manifests by themselves anymore. These manifests are going to be watched by Argo CD. And by default, if we have a new server or new changes to the Cluster API Tinkerbell provider will take care of all of these changes. So now, instead of making manual changes to your manifest and applying them manually, this is going to be taken care of by Argo CD. And I think that's pretty much it, close to the end of the presentation. So, just to recap, again, being quite repetitive here, but I want to really ingrain the message. With Cluster API, we have the capability of deploying infrastructure to any provider. With Tinkerbell, we have the ability to deploy bare metal anywhere. But the combination of these two, that means we can deploy our Kubernetes clusters on any bare metal machine. But more importantly, we already have strategies and initiatives in place to improve our automatic reconciliation for our YAML manifests. And all of this has been possible in the cloud-native ecosystem because everything is built on the building blocks principles. Pretty much, this is the engine that fuels the shape of the cloud-native landscape because it has the declarative, interoperable, and reliable principles at the basis. And that's pretty much it. Now, I do have a lot of this information. I have some demos as well, but they are going to be on my Medium blog post. So if you're curious about how Cluster API works by itself, if you're curious how Cluster API and GitOps works by themselves without Tinker, if you're curious how Tinker works, you can find all of these sections in my Medium blog post, so you can find all of it there. Now, I've put the link for the free course, the free Cloud Native Fundamentals course as well. So if you have anyone who would like to pursue a Cloud Native journey, they'll be able to do so out there. And if you have any questions, I know we're limited on time, but I am always available on Twitter and LinkedIn. You can always find me there. You can always kind of ask me questions out there as well. But so far, thank you very much.
Thank you, Kati. Maybe someone have any question? Great. First.
Hi. Thank you for this amazing session. As a complete newcomer to Tinkerbell especially, I have two questions there. One is, what are usually, in your experience, the difficult parts or components, or where do most people spend the most amount of time figuring things out? And the second part is the target cluster. Is having a Kubernetes cluster as an end goal always mandatory? That is, in other words, can I just use Tinkerbell in order to kickstart a bunch of servers for some other use case, like say an Hadoop cluster or something else?
So the first question is, where do we spend most time in terms of configuring our Tinkerbell server? Now, one of the important things with Tinkerbell, it's still in the sandbox level. So it requires still a lot of work and a lot of attention from the community. So I would say one of the frustrating part for me is currently, if I want to, I was actually planning a demo for everyone, but it's difficult to get it approved by my company. So I'm just going to talk for it, and maybe some of you can replicate it. There is a possibility to provision your local cluster with Tinkerbell using Vagrant. And one of the things is, even with the KPT provider, it still requires some tweaking and changes to always, there's still a failure chance. If you're running the same thing over and over again, there's still like a condition which is met, and errors to create your cluster. So I would say a lot of work has gone into the improvement of KPT, and this is definitely, if any of you are interested in this, please contribute. Honestly, it's all about open source. It's about contribution. It's about your involvement as well. So I would say the KPT provider still requires some work to make it as smooth. For example, AWS, it's running so splendidly. I have so many demos of AWS. I can provision a cluster like literally in 5 minutes with the creation of the VPC, with the creation of like all of my 4 or 5 instances. It's just like super quick. So I would say that requires more work. The second question was in regards to how can we provision our services using Tinkerbell, right? So that's the thing, like with Tinkerbell, you can provision any bare metal in any state that you want. My focus here was how can I provision bare metal Kubernetes. That was the idea. And this is why we install all of those binaries. So the target cluster is going to be the end for this particular talk. If you want to have bare metal, for example, with Hadoop installed of it, you can do that. It's going to be pretty much what you need to do is change your template set of actions. And this is how you will say, like, I want this binary on this operating system, and that's it. That's how you do it. So yeah, there is a possibility to do that.
I was just wondering, how does Tinkerbell compare to Rancher, for example?
So, the thing is, Tinkerbell is not the only infrastructure bare metal provisioner out there. You have tools, for example, you have Ironic from Red Hat. You have, as you mentioned, you have Rancher as well. The only difference here is Tinkerbell is open source. It has these 5 microservices. Usually, if you're talking about bare metal provisioning, you have this monolith, and it just does things for you. This, you have actually different services, which makes it easier for you to contribute and improve it all the way through. So open source being the microservice, which is by default nowadays. You have the microservice architecture, but by itself, it doesn't bring anything spectacularly new to the table. It just brings that possibility to integrate it with Cloud Native much more easier and provision your clusters and actually have templates very, very configurable. And you can do whatever you want with your bare metal. So I think this is the main difference out here. Thank you.
Katie, what do you think? How much power do those Tink components need? Raspberry Pis types, or yeah? But all right, thanks.
So how much power do you need for your Tinkerbell servers? The sky is the limit. But the minimum, I was even able to run on my machine, on my Mac, I was able to run a cluster with 3 nodes, which is good enough. But you have Raspberry Pis, that's splendid because you can define your hardware and then you can easily run templates on top of it. So yeah, Raspberry Pis are perfect for this. If I would have Raspberry Pis, like you have a suitcase, someone has a suitcase here with Raspberry Pis, and they're working with their server. So like if I would have that, I would definitely provide a demo. Yeah.
As you mentioned, kickstarting on AWS is a lot predictable, let's say, and accessible and understandable by most people. But bare metal is very custom to the companies, how they implement it and do these things. And due to various factors, like let's say the hardware itself has some faults or network has issues or whatever, certain nodes may not completely kickstart very well, right? So in that reconciliation loop, which the controllers are trying to get a fresh batch of servers to provision servers, if certain servers have issues, let's say 2 out of 40 of them have issues, what happens from the controller perspective? Do they just get marked as killed or failed or whatever? And how do we get back to it and fix what can't be fixed by the controllers and reinitiate that selectively?
So there are actually 2 types of reconciliation a node that has been failed with Tinkerbell provisioning. The first one, if we're talking about KPT, so if you want to install a Kubernetes cluster on top of it, the Tinkerbell provider for cluster API, if it's in a failure state, it will actually delete everything. So by default, it's going to be taken down. If you have a machine that's just provisioned with Tinkerbell, your bare metal, and has some binaries that you have, you can delete the workflow. That's it. So pretty much you delete the workflow, and this will restore it to the initial state. Yeah, so it should be pretty straightforward. Though, it still requires work. It's a sandbox project. Like, I really want to outline this. Like, one of the reasons I'm talking about this kind of projects is because I want to bring to your attention possibilities for you to contribute. Again, cloud native, it's all about contribution. When I started to talk about cluster API in 2019, it was literally at the beginning, and talking about it for 2 years. This project now is in beta stage, and they're moving to incubation and so forth, so it's doing very well. My same intention with Tinkerbell as well, because we have a growing desire or request to deploy your infrastructure to bare metal. We're not talking about startups anymore. They can deploy their infrastructure anywhere. We're talking about enterprise that have a requirement for bare metal. This is why Tinkerbell is going to be a very core project in the future, and this is why I want to raise awareness for it and for people to contribute. So, to answer your question, yes, you can delete the workflow, but at the same time, I still feel there's going to be a race condition somewhere, so just be careful of that. Don't try it on your infrastructure straight away. Take some Raspberry Pis. Yeah.
Thank you very much, Kati. No? No one else? Okay, in this case, thank you very much. Thank you to participate.